Hello everyone. Today we are to dive into the architecture of supercomputers and parallel processor. We are talking about multiprocessor network topologies. Think of it as a not as a one giant brain, but as thousands of smaller brains working together. But here's the catch. How do they talk to each other? If they can't communicate efficiently, they can't solve problems quickly, right? So today we will explore the blueprints, the topologies, which is used to write these brains together. So first of all, what exactly is an interconnection network? Imagine a thriving country. The cities are our processor and memory modules. And the interconnection network is the highway system connecting them all. If the highways are poorly designed, you get traffic jams and nothing gets delivered on time. So in parallel computing, this network is the absolute backbone. A slow network means a slow computer, no matter how fast the individual processors are. We look at the designs. First of all, how do we judge if a network is good or not actually? We use three main performance metrics: node degree, diameter, and bisection bandwidth. First is node degree. This is the number of cables plugging into a single processor. More cables mean higher cost and order complexity. And the next one is our diameter. Think of this as the worst case scenario. What is the longest path a message has to take to get from one side of the network to other? A smaller diameter means faster communication. Finally, bisection bandwidth. If you cut the network exactly in half, how many wires did you just cut? This tells us how well the network handles massive traffic jams when the half of the processors are talking to other half. Topology classification. Network topologies generally fall into two distinct families, static and dynamic. Static or direct networks are permanent. The wires are physically plugged from processor A to processor B. It's like a dedicated phone line. We mostly use these when processors are sending specific messages back and forth. The next one is dynamic or indirect networks. It uses switches like a traditional telephone exchange. The connections are built on the fly based on where the data needs to go. These are very popular in systems where all the processors share a massive pool of memory. Look at some static designs you might actually recognize. The 2D mesh is incredibly common. It's laid out like a city grid. It's very easy to build on a silicon chip. However, if you are on the edge of the grid, you have fewer neighbors. To fix that, we create a structure called torus. Imagine taking that flat city grid and wrapping the top edges to the bottom and the left edges to the right, like the map in the game Pac-Man. Now, everyone has exactly the same number of neighbors, and if you just take a single line of processor and connect the ends, you get a ring. Simple, right? But the diameter can quite long if you have a lot of nodes. Now, let's step into higher dimensions with a binary hypercube. This sounds like science fiction, but it's a brilliant mathematical design. In a hypercube, every processor is given a binary address, like 001 or 10 like that. You connect two processors only if their addresses differ by single bit. Why we do this? This is called logarithmic scaling. If you double the number of processors, the maximum distance a message has to travel only decreases by 1. It is an incredibly powerful way to connect thousands of processors without creating a massive traffic delay. Let's put them all side by side. Look at this table. Notice how a ring has a cheap fixed degree of 2, but its diameter grows terribly as you add nodes. That is n by 2. And the mesh is great middle ground, keeping the degree at 4, but the diameter still grows somewhat linearly. Then look at the hypercube. It supports a massive number of nodes with a tiny diameter of size log n, and the trade-off. The degree grows as you scale, meaning the hardware becomes very expensive and complex to wire up. There is no perfect network, so it's all about trading cost for speed. Let's moving to the dynamic networks. The absolute gold standard is the crossbar switch. Imagine a grid where every row is a processor and every column is a memory module. At every single intersection, there is a switch. This means every processor can talk to every memory module at the exact same time without waiting for each other. It's called non-blocking. It is incredibly fast, but it requires n squared switches. If you have 10 processors, you need 100 switches. If you have 1000 processors, you need a million switches. It's too expensive for massive systems. Multi-stage networks. Because crossbars are too expensive, engineers created a compromise called multi-stage interconnection networks, like the Omega network shown in the diagram. Instead of one giant switch, we use multiple stages of tiny 2 cross 2 switches. Messages route through these stages step by step. You don't get the perfect non-blocking performance of a crossbar, meaning sometimes two messages might want the same wire at the same time, but it drops the cost from n squared to n into log n. It gives us 90% of the performance for a fraction of the hardware cost. This is what you will find inside many modern internet routers and shared memory computers. To wrap up, designing a multiprocessor computer is a delicate balancing act. Do you need the raw speed of a crossbar, or the cheap scalability of a mesh, or the mathematical elegance of a hypercube? The choice always comes down to how many processors you have and how much delay your software can tolerate and your budget. Thank you so much for your time. Are there any questions about how these networks operate? Leave in the comment section. Thank you.